Okay. So, I want to consider a special case and assume the forward amplifier only has odd order nonlinearity. Right? That basically means that A2 is 0. Then what comment can we make? V out is approximately 1 over f V I plus A3 V I cube by A1f whole power 4. Now, what comment can we make about so can we get any into, I mean, why does this result make sense? In other words, remember what is the third harmonic distortion? HD3 is proportional to the third order, the coefficient of the third order term to the coefficient of the first order term. It's proportional to amplitude square, right? But what is that constant which multiplies the amplitude square?
That is the
3A3 by A1, right? And what is the 3A3 here? In this case, it is nothing but A3 by A1f whole power 4 divided by 1 by f. Right? Okay. So, the question I would like to ask or understand is, so this is telling us that if I double the amplitude, I mean sorry, if I double A1, keeping, I mean let us say 1 over f is not changed because I want the same closed loop gain. If I double the loop gain, correct? So, if I double A1, the this thing goes down by a factor of 16. HD3 goes down by a factor of 16. So, why does that make intuitive sense? What happens when, so let us draw our amplifier again, let me copy and paste it. Right. So, what this analysis is telling us is that if A1 doubles, correct, the harmonic distortion is going down by a factor of 16 for the same, you know, A3 and the same 1 over f. So, intuitively, why do you think, first of all, why should the distortion reduce if A1 increases? Increases, so what?
So, non-idealities it will suppress.
I understand, but yeah, why will it suppress non-idealities?
That error voltage will be less.
So basically, when you increase A1, right? Well, let us say, I mean, think about it this way: the error voltage here is approximately the output voltage divided by A1, correct? So, if I double the, so this voltage,
A1 is double means error voltage will come.
see if A1f is very large, the output voltage is approximately Vi by f, correct? If the output voltage is Vi by f, what comment can you make about the error voltage?
Like Vi by AF.
You can, I mean,
Like approximately.
Vi by A1f, correct? All right. Now, if I double A1, what will happen to the error voltage?
It will become off.
it will become half.
And output it will be like that A3 term will depend on the cube, so it will become like 1 by A, it will become 1 by 8. And here also A1 like overall output dependence on the third order Vi cube will be reduced by 8 times.
I mean, so a simple minded analysis will, so here is my within quotes false argument, right. The argument is very subtle, which is why I wanted to discuss this. And it's got nothing to do with current injection. Well, if you go and do the an exhaustive analysis and set the limit for A1F being large, you will get the same result. Current injection is simply a simpler way of getting at the same result, right. But what I am going to discuss now is basically what I would call a side thing, but it's sufficiently interesting in its own right that I thought I'll include it here since we are on the topic. So, if the loop gain is very large, right. So, A1F is much greater than 1. So, the output is approximately Vi by F. If the output is Vi by F, the error voltage to a very good approximation is Vi by A1F, correct. So, if the error voltage is Vi by A1F, the output of the forward amplifier, the cubic term, right, must go as A3, or rather the output distortion. Basically, you can think of it as the error voltage is being amplified by the amplifier, correct. So, Vi by A1F is getting processed by an amplifier with A1 VE plus A3 VE cube. So, it seems reasonable that the output will be basically Vi by F, which we knew already, the fundamental term, but the third order term should be shouldn't the third order term be proportional to A3 times VE cube, which is Vi cube by A1F the whole cube, right. I mean, there is another F cube, I believe, right. Sorry, no, Vi by A1F, yeah, that is it, okay. And this is telling us that if you double A1, the output distortion should go down by a factor of 8, right. However, our careful analysis shows that it goes down by a factor of 16. So, you have an additional power of loop gain coming in there, right. In fact, I do not know if you noticed it, but even for the second, I mean the same argument for a second order distortion. Yeah, so we saw that with second order distortion, well, the error will be the error term will be A2 VE square, and that should go as according to our simple minded analysis, it seems very reasonable that it should go down by A1F the whole square, but it actually goes down by A1F the whole cube, right. Third order, it seems like I hope I have just convinced you that it should go down as A1F the whole cube, but the actual analysis is showing us that it is going down as A1F whole power 4, right. And it turns out that the argument is subtle, and I would like to before I show you that argument, I would like to explain this graphically. So, let us assume you have a negative feedback system. This is linear. So, this is VE, this is VO, V out I would say. Right. So, if we wanted to find the output as a function of the input, so we would basically say VE is Vi minus F times V out, and V out is nothing but A1 times VE. So, if you want to do this, I mean, we are eventually going to move to a situation where the amplifier is non-linear, right. So, which is why we want to use a graph to solve it. So, what will we do if we wanted to solve this using solve this graphically? We will plot V out on the y axis and what do you call V e on the x axis, right, and we will so we will plot equation 1 and equation 2 on this graph, and where the two of them intersect will tell us what the output is and what the so V out is A1 times V e. So, that is nothing but a straight line with a slope A1, correct. So, this is V out is A1 times V. What is the this equation? How does it how do you plot that? You can see that this can be rewritten as V out equal to V I by F minus V by F, correct. So, that basically means it is a straight line with a slope of minus 1 by F, right. All right, and the what do you call the intercept on the y axis must be V I by F, correct, and which is the solution? Yeah, this point is the point of intersection, that is the solution. And if you do this you can just use simple geometry to basically figure out that this is going to be V I by 1 plus A1 F. Does that make sense? So, as A1 keeps increasing, if the slope keeps increasing, what comment can you make about the point of intersection?
It will move towards the y-axis.
It will move towards which point on the y-axis?
That VI by F point.
It will move towards the Vi by F point on the x-axis. Okay, all right. Now, let us assume that and what happens as you keep changing the input?
That intercept point will be.
Yeah. So, as you keep changing Vi by F, what will happen? This line, the blue line, will move parallel to itself, right? And the point of intersection will basically also move, okay? And likewise, the error voltage will also move. All right. Now, let us say so if I go on increasing Vi from a small value, so let us say this is a small Vi, right? The point of intersection is here, right? And this is that error voltage corresponding to a small Vi, right? So, Vi2, let us say this is Vi1 by F, and that is the output, correct? So, if of course, if both of them are straight lines, I mean if everything is a straight line, then if I keep increasing Vi linearly, the error voltage will increase linearly and the output will also increase linearly. Now, let us say the characteristic of the amplifier is non-linear, right. So, instead of doing this, right, like most saturating amplifiers, let us say there is some compression. So, I will use a different color here, right. So, this is in reality, of course, the compression will be a lot smoother, but this is good enough to illustrate the point. So, as you keep increasing Vi and you plot the error voltage, what comment can you make about the error voltage? So, up to here, this is the critical Vi at that break point, right. So, if I plot V error versus Vi, right, until you reach that critical error, what comment can you make about the point of intersection? It will go linearly, right. So, beyond, if the input increases beyond the critical magenta line there. So, in other words, if the input increases beyond that point, what comment can you make about the point of intersection?
Like error voltage, it will be not increased, like their gain will be reduced.
See carefully.
Error voltage will increase, but
okay, now hold on. So, this is the red line shows the output, the characteristic of the amplifier without any nonlinearity, right, or without any saturation. Now, the magenta line shows the output with saturation, correct. So, what is the error voltage without saturation?
error, that is Vi by A1.
That is, this corresponds to this point. What is the error voltage with saturation?
It is much higher than.
So, with saturation you can see that the error voltage is much higher. So, if I plot the error voltage as a function of input, what will you get?
It will increase with the higher slope than the.
Correct. Right. So, why is this happening? Well, the negative feedback loop is desperately trying to make the error voltage 0, correct. So, if the gain is very high, a small error voltage is enough to make the output V out times F equal to Vi. Now, as you go on progressively increasing the amplitude of the magnitude of the input, the forward amplifier's output is not as high as it would have been if it was perfectly linear. So, the output is actually reducing with respect to an ideal linear amplifier,
To get that same.
right. So, the negative feedback loop, in an attempt to reduce that VE, right, or to make V out times F equal to Vi, the only way it can do it is to overdrive the amplifier, right. So, if the amplifier characteristic is compressive, right, the error voltage that is developed at the input of the amplifier becomes expansive, right, because the negative feedback loop is basically trying its best to undo the nonlinearity of the amplifier, right. Of course, it can only work if the gain of the loop gain is becomes close to infinity. So, it tries its best. So this is basically so in other words, this error voltage is not merely equal to V out by A1, right. It also has got a component which is basically pre-distorted to make to try and undo the nonlinearity of the amplifier, because it is trying to make the input and output that V out times F equal to Vi, right. So, that gives you an additional factor of loop gain, right, which is why you get an extra factor. It is not merely, it is very simple to think, very straightforward, it is appealing intuitively to think that the error voltage at the input of the forward amplifier must reduce if I increase the loop gain. That is correct, right, but that only gives you a factor of loop gain the whole cube, correct. But because of pre-distortion of the negative feedback loop, you are actually getting an additional factor of A1F, right, which is why whether you look at the third order nonlinear term or the second order nonlinear term, remember that the third order nonlinear term is proportional to 1 by A1F whole power 4, right. and likewise the second order term is proportional to
1 plus a1f
a1f the whole cube, right. Though you would expect, if you simply went by the argument of a smaller swing, you would basically get only 1 by f square is what you would expect, but you get 1 by f the whole cube, right. So, with that we will stop today, we will continue in the next one.